Welcome back to the deep dive. Today, we're tackling a challenge that I think every single machine learning practitioner eventually just smashes their head against.
Okay.
Imbalanced learning,
Yeah.
specifically in the tabular domain. But I want to be really clear up front.
Yep.
We are not here today to talk about the basics of SMOT. We're not going to cover random undersampling or, the first principles of focal loss.
Right. We're assuming if you're listening to this, you're past that. You've been there, done that, and seen it fail.
Exactly. You already know that just duplicating your rare samples or cranking up a class weight in your loss function is, well, it's rarely the silver bullet you hope for.
It almost never is. Everyone knows that if you have 100 to 1 or, 1,000 to 1 class ratio, your classifier is just going to get lazy. It'll optimize for the majority and pretty much ignore the minority class completely.
That's the baseline. That's day one of an imbalanced learning course.
Right. What we're interested in today and why we're doing this deep dive is why the next level of solutions, the more advanced data cleaning and resampling techniques we've all relied on for decades, why they also fail when the data's geometry gets messy.
And to do that, we're dissecting a paper that I think fundamentally reframes the issue. It's titled Geometric Manifold Rectification for Imbalanced Learning, or just GMR for short.
By Wang, Lai, and Jia. And it really does shift the paradigm.
It does. Their core argument is that for years we've been treating imbalance as a counting problem, a problem of ratios.
I don't have enough red dots, so I need more red dots.
Exactly. But this paper argues very convincingly that we should be treating it as a topological problem, a geometry problem.
That distinction right there is the entire ballgame. Topological intrusion, that's the phrase they use, and it's such a powerful mental model.
It really is.
The issue isn't just that there are fewer minority samples. It's that the majority samples have, in a very real sense, physically invaded the geometric space, the manifold of that minority class. They're trespassing.
So our mission for this deep dive is to rigorously unpack GMR. And there is a lot of ground to cover here. We're going to have to critique the failure of what they call symmetric cleaning methods, things like ENN and Tomek links that we're all familiar with.
Yeah, the classics.
Then we need to break down the mathematics behind their two-part solution. First, this idea of geometric confidence estimation.
Which is a much smarter way of trusting your data points.
And second, the core algorithm, which they call adaptive asymmetric cleaning.
And we have to spend a good amount of time on the theory behind their threshold choices. I mean, why do they set the majority removal threshold, which they call alpha, so much lower than the minority protection threshold, beta?
Right. It's not just a lucky guess or some hyperparameter they tune.
No, not at all. It's grounded directly in the mathematics of asymmetric risk minimization. It's a principled choice.
Precisely. And we'll finish up by looking at the experimental results, which are pretty compelling, including how this whole framework integrates with, believe it or not, tabular diffusion models.
Which is very, very cool.
But let's start where the paper starts, at the core problem, this idea of topological intrusion.
Okay.
The paper has this great visualization, it's figure 1, that just frames it perfectly. I mean, in a textbook machine learning problem, your classes are nicely separated by a clean line or a hyperplane.
Yeah, the dream scenario. But in any high-stakes tabular data problem, we're talking fraud detection, medical diagnosis, churn prediction, it's never, ever that clean.
Never. What you have instead is what the authors call the overlap region.
So let's try to visualize this. Imagine you're in some high-dimensional feature space. You have this massive, dense cloud of majority samples. Let's call them class 0, the blue circles.
And somewhere in that space, you have this tiny, sparse scattering of minority samples. Class 1, the red squares.
Now, in this overlap region, the blue circles aren't just near the boundary of the red squares, they're mixed in. They are physically co-located with them.
Yeah.
Some of them are just noisy majority points, but their presence totally corrupts the local neighborhood.
And this is where that term you mentioned, intrusive samples, comes into play.
Exactly. An intrusive sample is a majority instance, a blue circle, that has effectively crossed over the true underlying decision boundary. It's landed in territory that should belong to the minority manifold.
And because the majority class is so much larger, this becomes a huge problem very quickly.
It's just a numbers game. Let's say your data has a really low noise rate, maybe only 1%.
Okay.
If you have 1 million majority samples, that 1% still gives you 10,000 noise points. Now, if your entire minority class only has, say, 500 total samples.
Those 10,000 majority noise points are going to completely overwhelm the 500 true minority signals.
They dominate the landscape. The noise from the majority completely drowns out the signal from the minority, and it happens in the most critical area, the overlap region, where the classifier has to make its toughest decisions.
So the noise isn't just random. It's concentrated exactly where discrimination is hardest. That's the problem GMR sets out to solve. But to appreciate their solution, we have to really dig into why our current tools fail at this.
Which brings us to their first big section, the failure of symmetric cleaning.
Let's talk about the classics. I mentioned them before. Edited Nearest Neighbours, ENN, or the Neighborhood Cleaning Rule, NCR, TOMEC links.
Yeah, these are foundation methods that have been around since the 1970s, some of them.
And they all work on a pretty simple, intuitive logic, right? You look at a sample, you check out its local neighborhood.
And if the majority of your neighbors disagree with your label, the algorithm concludes you're probably noise and removes you.
It sounds so reasonable. If I'm a blue dot and I look around and I'm surrounded by a sea of red dots, I'm probably in the wrong place.
Yep.
Get rid of me.
And for balanced data, that logic is perfectly fine. It works. But for imbalanced data, it is absolutely catastrophic.
Why?
The paper identifies the core issue as symmetric treatment of asymmetric costs.
Okay, let's unpack that. We know that in any serious imbalanced problem, the cost matrix is heavily skewed.
Right.
The cost of a false negative, let's call it C01, is much, much higher than the cost of a false positive C10.
Of course. Missing a cancer diagnosis is infinitely worse than flagging a healthy patient for a follow-up test. Missing a $1 million fraudulent transaction is way worse than briefly freezing a legitimate customer's card.
But the problem is that symmetric cleaners like ENN, they don't know that. They have no concept of this cost matrix.
To them, all errors are equal, so they treat a noisy majority sample and a hugely informative minority sample as equally disposable.
So let's walk through that. Imagine one of our precious minority samples, a red square that's sitting in that overlap region. By definition, it's going to be surrounded by a lot of those intrusive blue majority samples.
Okay.
ENN comes along, looks at its 5 nearest neighbors, sees maybe 4 blue and 1 red, and says, well, the neighbors disagree, and it just deletes the minority sample.
That's what the paper calls false positive cleaning, and it's devastating. You have just actively pruned away the very signal you are so desperate to preserve.
You're cleaning away the minority class because, from a purely local and naive perspective, it looks like noise relative to the overwhelming number of majority samples around it.
Exactly. The paper's argument is simple. Retaining a noisy majority sample is, an annoyance. It might lead to a false positive later. But removing a scarce, potentially critical minority sample is fatal to your model's performance. You simply cannot apply a symmetric rule when your underlying risk profile is fundamentally asymmetric.
So that's the first and maybe biggest flaw, but they identify a second, more subtle technical flaw in how these algorithms even count the neighbors in the first place.
Right, this gets into the weeds a little bit, but it's really important. They critique the uniform voting mechanism that's inherent in almost all standard KNN-based methods.
The Parson-Rosenblatt window issue?
You got it. So most of these cleaning algorithms, they start with a standard KNN search. Let's say you set K to 5. The algorithm finds the 5 closest data points.
And then it takes a vote.
It takes a vote. But in that voting process, all 5 of those neighbors get to contribute equally to the final decision.
One neighbor, one vote. Simple democracy.
Simple democracy, but it's a terrible model for local geometry. It rests on this massive unspoken assumption that all 5 neighbors are equally informative.
Which they almost certainly are not.
Never. Imagine you have your query point, X. One neighbor, X1, is extremely close to it. I mean, they're practically sitting on top of each other in the feature space. Another neighbor, X5, is way out at the very edge of that KNN search radius.
Okay.
In a uniform voting scheme, that distant neighbor, X5, has the exact same influence on the decision as this super close neighbor, X1.
And if you're in that messy overlap region, that distant neighbor is far more likely to be one of those intrusive majority samples or just some other kind of noise.
Precisely. The spatial distribution of labels in the overlap region is what we call heterogeneous. It's not smooth. The neighbors that are physically, geometrically closer provide much, much stronger evidence about the true label distribution right at point X.
So they should get more say.
They should get way more say. The distant neighbors, they're just introducing variance and noise into your estimate. By treating them all equally, Standard methods are essentially calculating a very low-resolution, high-variance estimate of the local posterior probability. They look at a neighborhood and see a confusing mess because their measurement tool, their lens, is just too blurry.
Okay, so just to recap before we move on, we've got two fundamental failures of the classic approach. First, symmetric cleaning, which completely ignores the asymmetric cost of errors.
Leading to the deletion of precious minority samples.
And second, uniform voting, which ignores the local spatial geometry, leading to noisy and unreliable neighborhood analysis.
Exactly, and that's the perfect setup for what GMR proposes to do instead.
Geometric manifold rectification.
Let's get into it.
So let's look at the first pillar of GMR. This is how they solve that blurry lens problem, the voting problem. They call it geometric confidence estimation.
And the core idea is to move from that flawed uniform voting to an inverse distance weighted voting scheme.
Now, weighted KNN isn't a brand new idea in itself.
No, it's been around. But the way they apply it here and the theory they build around it is the key. They define a very specific kernel function. It's equation 4 in the paper. It's simple. K of xi, xj equals 1 over the distance between them, plus a tiny epsilon.
Right. The epsilon is just a small constant to stop you from dividing by 0 if 2 points are identical.
Exactly. But think about the behavior of that function, 1 over d. As the distance, d, gets very, very close to 0, the weight, k, shoots up towards infinity. It's a hyperbolic curve.
So points that are extremely close get an enormous weight, and points that are even a little bit farther away see their influence drop off dramatically.
It creates what they call a geometric confidence score that is hypersensitive to the immediate locality of the point. It effectively listens very, very closely to the nearest 1 or 2 neighbors and almost completely ignores the more distant neighbors within that K-set.
But crucially, they don't just say, hey, this feels better. They actually provide a strong theoretical justification for why this is the right thing to do.
This is theorem 3.3 in the paper, geometric weighting and variance reduction. And it's a really elegant piece of theory.
So what's the argument?
They start with a premise that I think we would all intuitively agree with. They assume that conditional label noise is heteroscedastic.
Meaning the noise level isn't constant across the feature space.
Right. And specifically, they assume that the noise level increases as the distance from your sample increases. The further away a neighbor is, the less reliable its label is as a proxy for your current sample's label.
Which just makes sense. If I'm trying to figure out the price of my house, I should trust the price of the house next door way more than the price of a house 5 miles away.
Exactly. I'm importing more uncertainty, more variance into my estimate if I trust that distant neighbor. So what theorem 3.3 does is it formally proves that if this very reasonable assumption holds, if noise correlates positively with distance, then a distance decaying estimator, like their inverse distance kernel, will strictly reduce the variance of your posterior probability estimate compared to a uniform one neighbor, one vote estimator.
So in mathematical terms, you're minimizing the mean squared error, the MSE, of your probability estimate.
That's it. You're denoising the confidence score itself before you even think about making a decision to keep or remove a sample.
And in that chaotic overlap region, reducing the variance of your estimate is probably the single most important thing you can do.
Absolutely. You need a stable signal. You need to listen to the true signal, which comes from the very close neighbors. And you need to aggressively mute the noise, which comes from the more distant one.
Okay, but there's a catch here, and it's a big one that plagues all distance-based algorithms. We're dealing with tabular data. And tabular data, especially wide data, often suffers from the curse of dimensionality.
Ah, yes, the bane of every data scientist's existence.
The paper even references the classic work by Bayer and others from 1999 on this topic, the concentration of measure.
Right. And for anyone who needs a quick refresher, as the number of dimensions, D, in your dataset increases, the volume of the feature space expands exponentially.
Which makes the data incredibly sparse.
But maybe more counterintuitively, the distribution of pairwise distances between points starts to concentrate. The distance to a point's nearest neighbor and the distance to its farthest neighbor begin to converge.
In very high dimensions, every point is roughly equidistant from every other point.
It's a bizarre but true property of high-dimensional space, and you can see why that's a problem for this method.
Well, yeah. If all the distances d are roughly the same, then your inverse distance weight, 1 over d, basically becomes a constant.
And you degrade right back to the uniform voting scheme you're trying to escape. Your geometric advantage just evaporates into thin air.
So how does GMR handle this? Because this seems like a fatal flaw.
They implement a really clever and pragmatic solution they call adaptive metric selection. It's laid out in Corollary 3.4 of the paper.
It's not some complex new metric. It's essentially a heuristic toggle switch.
It is,
Yeah.
but it's a well-justified one. The rule is simple. If the number of dimensions, d, is less than or equal to 100, they just use the standard Euclidean distance, the L2 norm.
Which works perfectly fine for lower dimensional manifolds when distances are still meaningful.
But if d is greater than 100, they automatically switch the distance metric to angular distance.
Which is essentially 1 minus the cosine similarity.
Exactly.
So why does cosine distance survive the curse of dimensionality when Euclidean distance fails?
Because cosine distance isn't measuring the magnitude of the separation between 2 points. It's measuring the angle between their vectors. It's about directionality. So even in these bizarre high-dimensional hyperspheres, where all the Euclidean norms are concentrating and losing their discriminative power, the direction of the vectors often remains very informative. 2 data points that are conceptually similar will still point in roughly the same direction, even if the space is sparse.
So by measuring 1 minus the cosine of the angle, you're still capturing that similarity.
You are. And by automatically switching to this more robust metric in high-dimensional spaces, GMR ensures that its geometric confidence estimation remains reliable and effective even in very, very wide data sets, like the kind you might see in genomics or with, high-dimensional text embeddings.
That's very clever. So to sum up this part, we now have a robust, variance-minimizing, and dimension-adaptive way to estimate the confidence of each data point's label based on its true local geometry. We know who to trust.
We have a high-resolution lens.
Which means we can now move to the core of the algorithm, adaptive asymmetric cleaning.
This is where we fix that first flaw, the symmetric treatment of asymmetric costs.
And the whole design philosophy here can be boiled down to a simple mantra.
Strict on the majority, conservative on the minority.
Let's break down the cleaning rules in detail because the specific thresholds they choose are, as you said, central to the paper's theoretical contribution. First up, majority cleaning. How does it work?
So the GMR algorithm iterates through every single sample in the majority class, class 0. It flags a sample, xi, for removal if it meets one of 2 conditions.
One of 2, so it's an OR condition.
Correct, an OR condition.
Yeah.
Condition 1 is simple inconsistency. The algorithm calculates the geometric confidence score, and if the neighbors vote for the other class, so if y hat is not equal to y, the sample is flagged for removal.
Okay, that's pretty standard. That's what ENN does, more or less.
It is, but it's condition 2 that's the really interesting part. They call it the ambiguity rule. Even if the sample is technically classified correctly by its neighbors, GMR then checks its actual confidence score, the estimated posterior probability that it belongs to the majority class, P of y equals 0 given xi. If that confidence score is less than a threshold, which they call alpha, the sample is also flagged for removal.
And the default value for this alpha threshold is 0.3.
Right, 0.3. Now, stop and think about the implication of that for a second.
Okay.
Let's say a majority sample has a confidence of, say, 0.25. Now, wait, let me rephrase that. The confidence in its own class. So if PYLI is, say, 0.4, it's still a majority vote.
Right. 0.4 is less than 0.5, but its neighbors are not voting for the other class. It's just not a confident vote.
Let's be more precise. The confidence for its own class is PYARXI. The rule is to remove it if this confidence is less than alpha. Right, that's not right. The paper says PYXXA alpha for removal. That's the minority class, isn't it? Let me check. No, my mistake. It's simpler. Remove if misclassified OR if its confidence in the majority class, PYAXI, is less than alpha. Wait, that still feels wrong. Let's reread the rule. Okay, for majority, remove if misclassified OR if its confidence in its own class, PYXI, is less than alpha. So if PYXI is 0.4, it's safe. But if it's 0.2, it's removed. The paper actually says PYXII, the confidence in the minority class. Let me get this straight from the source. Okay, I see. My apologies. The rule is this. For a majority sample $6, it's removed if it's misclassified. So Y as Y. If its confidence in its own class, PXII, is less than the threshold. They don't use alpha there. They use alpha for the minority class. This is confusing. Let me reread section 3.3.
Take your time. This is the core of it.
Okay, found it. My apologies to the listeners. The notation is dense. The rules are as follows. For a majority sample, $6 in DMI, you remove it if it's inconsistent, misclassified by neighbors, or if it is ambiguous. They define ambiguity as its confidence in the majority class, being less than alpha.
Okay, so if the confidence in its own class drops below 30%, no, wait, the default for alpha is 0.3. So is that the right way to think about it? Let's check the table.
I see, table 2. They have different thresholds. Let's stick to the main text. E pi aller for majority removal.
Right. Let's start over on the rules to be crystal clear. It's actually simpler. They calculate one score for everything. Py one side the probability of being in the minority class. For a majority sample where 1 y, it's removed if py 1 a lie.
Okay, so if its estimated probability of being a minority sample is greater than 30%, since alpha bias 0.3, it's considered ambiguous and gets removed. Exactly. Even if its neighbors still technically vote majority, if there's a 31% chance it's a minority, GMR says, that's too ambiguous for a majority point. We have plenty of you. You're cluttering the boundary. You're gone.
It's being extremely strict. It's aggressively carving out space anywhere near the decision boundary.
Aggressively. Now, contrast that with the rule for the minority class, the minority protection rule.
Okay.
For a sample in the minority class, the algorithm is, as the name implies, extremely protective. A minority sample is flagged for removal only if 2 conditions are met simultaneously. It's an A and D condition.
An A and D, so it's much harder to get removed.
Much harder. First, it must meet the inconsistency condition. It has to be misclassified by its geometric neighbors.
Okay, so if it genuinely looks like noise from a local perspective, we will consider removing it.
We consider it, but then it has to pass a second, much tougher condition, which they call deep noise. The algorithm checks that same score, P say Y. It is only removed if that probability is less than a threshold beta dollar.
And the default for beta is 0.7. Wait, let me check that again. No, the paper says it's removed if PY1 beta, so if its confidence in its own class is less than 30%.
Yes, that's it. It's PY1 beta. With beta dollars and 77 cents, that means it's only removed if its confidence in being a minority class member is less than 0.3. In other words, the algorithm has to be more than 70% sure it's actually a majority sample that has been mislabeled.
So to delete a precious minority sample, you need proof beyond a reasonable doubt. You need overwhelming evidence that it's just an intrusion from the majority class that somehow got the wrong label.
Precisely. Now let's talk about those thresholds, because this is the theoretical heart of the paper. We have alpha equals 0.3 for the majority rule, and beta equals 0.7, which defines the minority rule. Why is alpha so much lower than beta? Why this big gap between them?
This is the asymmetric risk minimization you mentioned earlier.
This is it. It all comes back to that skewed cost matrix. The cost of a false negative, theta inch arrow, is much, much greater than the cost of a false positive C10. Data cleaning is, in effect, a pre-classification step. Every time you remove a point, you're making a decision. You're classifying it as noise.
And that decision has a cost associated with it.
It does. If you mistakenly remove a valid minority point, you are directly contributing to a false negative outcome for the final classifier. You've destroyed the evidence it needed. If you fail to remove a noisy majority point, you are contributing to a potential false positive.
So the thresholds you use for cleaning must reflect the downstream costs of the errors.
They absolutely must. The gap between alpha 0.3 and beta 0.7 creates this crucial zone of tolerance, specifically for the minority class. By setting alpha low at 0.3, we are being strict on the majority. We are saying any majority sample that has more than a 30% chance of belonging to the minority class is too ambiguous, too risky to keep. We will treat it as a potential intrusion and clear it out.
We accept a higher risk of incorrectly removing a valid majority point, a false positive in the cleaning step, in order to guarantee a cleaner, safer space for the minority.
Exactly. And conversely, by setting beta high, in 0.7, we're being conservative with the minority. We are saying we cannot afford to lose a single one of these samples unless the evidence that its noise is overwhelming. Even if a minority sample's confidence in its own class is only, say, 40%, meaning it's technically misclassified by a 60-40 vote, we keep it.
Because the cost of being wrong and deleting it, if it was actually a valid signal, is just too high to bear.
So the inequality alpha is less than 1 minus beta, or 0.3 is less than 0.3. Wait, that can't be right. Let me reread the paper's motivation for alpha beta. This is critical. Okay, section 3.4. The thresholds are used differently.
Alpha, remove if it looks too much like a minority.
PY-VSD, 1 beta. Remove if it looks way too much like a majority. No, that's not it either. Let's find the exact rule. Okay, I have it. It's much simpler. I was overcomplicating it. For a majority sample, remove if misclassified in its confidence in the majority class, PY-ST can't pay. For a minority sample, remove if misclassified in its confidence in the majority class, beta. Okay, this makes sense.
Okay. So let's walk through that with the default values. Alpha, $3 and $3, 3 error 7 cents.
For a majority sample, we first check if its neighbors disagree. If they do, we then check its confidence in being a majority sample, P by where 6 and 3 Harai. If that confidence is less than 0.3, it's gone.
So it has to be misclassified and have very low confidence in its own label. That's a strict rule.
It is strict. We're saying if you're in the wrong neighborhood and you're not even sure you belong to our class, you're out. It purges the most ambiguous majority points.
Okay, now for the minority.
For minority sample, we first check if it's misclassified. If it is, we then check its confidence in being a majority sample. P-gallery is a 2-out time. It is only removed if this value is greater than 0.7.
So it has to be in the wrong neighborhood, and the algorithm has to be over 70% sure that it's actually a majority member.
That's the burden of proof.
Yeah.
The inequality alpha beta is the mathematical encoding of the asymmetric cost. We set a low bar for removing ambiguous majority points and a very, very high bar for removing ambiguous minority points.
It shifts the entire risk profile of the cleaning process to align with the risk profile of the business problem.
That is the entire theoretical motivation. This asymmetry is not a heuristic. It's a direct consequence of wanting to minimize asymmetric risk.
And there's one final safety net built in for the minority class, right? The safeguarding cap.
Yes, which they call gamma. And this is just a hard constraint, a common sense emergency brake. GMR will never, under any circumstances, remove more than gamma % of the total minority class samples. The default is 10%.
So even if, in some bizarre data set, 20% of the minority samples meet that incredibly strict deep noise criteria.
Even then, if 20% of them qualify for removal, GMR will simply rank them by how noisy they are, by their confidence in the majority class, and it will only chop off the worst 10%. It prioritizes preserving the manifold over perfect cleaning.
And there's an even more extreme case.
Yeah, if the absolute number of minority samples is tiny to begin with, the default is less than 10, it just disables cleaning for the minority class entirely.
To prevent what they call manifold collapse?
Exactly. You can't learn the geometric structure of a class if you delete all of its members.
Okay, this is a very sophisticated set of rules.
Right.
Which brings us directly into the next section of the paper, the theoretical foundations. They argue that this whole cleaning process doesn't just, tidy up the data. It fundamentally reshapes the entire posterior probability landscape.
Yes, and this is lemma 3.2. The data cleaning effect.
This part is fascinating.
It really is. It formalizes this idea of posterior shifting. The lemma states that if the removal rate of the majority class, which we can call R0, is significantly higher than the removal rate of the minority class, R1.
Which GMR is explicitly designed to ensure through those asymmetric alpha and beta thresholds.
Then the empirical posterior probability of the minority class, P of y equals 1 given x, is monotonically increased across the cleaned dataset.
Let's try to visualize what that actually means. We're in that messy overlap region. Before GMR, it's a mix of blue and red dots, but it's heavily dominated by the blue, the majority.
Right, so if you pick a random point in that region, the probability of it being red is very low.
But then GMR comes in. It applies its strict rule to the blue dots, aggressively pruning the ambiguous ones near the boundary.
And at the same time, it applies its super conservative rule to the red dots, protecting almost all of them.
So the local density of blue dots drops significantly, while the local density of red dots stays more or less the same.
Which means the ratio of red to blue in that local area has just shifted. The probability of red goes up.
You're artificially, but very intelligently, boosting the signal-to-noise ratio, but only in the specific regions where it matters most.
That's it. And this directly leads to their big theoretical payoff, which is Proposition 3.5, asymmetric boundary alignment.
This is the proposition that connects the data cleaning step to the actual classifier you train afterwards.
Exactly. The proposition says that if you train any standard classifier, a logistic regression, an SVM, a decision tree, it doesn't matter on this GMR rectified data, the decision boundary that it learns will be physically different. Because the posterior probability, P of y equals 1 given x, has been artificially increased in that overlap region, the line where the classifier decides between classes, the P equals 0.5 decision boundary, has to move. And it moves toward the majority class.
It literally expands the decision space for the minority class.
Yes. You could think of it as physically pushing the border fence deeper into the majority's territory.
Which, in practice, means the classifier will be less likely to misclassify a minority point. It reduces false negatives.
The geometry of the learned decision boundary is now aligned with the asymmetric cost objective of the problem you're trying to solve. It's a really beautiful connection between data pre-processing and the final model's behavior.
Now, a skeptical listener might be thinking right now, okay, this is clever, but why go through all this geometric trouble? Why not just use cost-sensitive learning? Why can't I just crank up the weight for the minority class in my loss function and achieve the same thing?
That is the standard and very fair counterargument, and the paper provides a really compelling answer.
What is it?
Cost-sensitive learning, or reweighting, operates on the original, noisy, topologically invaded data. So if you have those intrusive majority samples, those blue dots deep inside the red manifold, and you tell your loss function that getting them wrong is extremely expensive,
The classifier is forced to overfit to them?
it has no choice. It will try to weave an incredibly complex gerrymandered decision boundary around those individual noise points just to satisfy the extreme demands of the loss function.
You're essentially forcing your model to memorize the noise, which will lead to terrible generalization.
Exactly. GMR's philosophy is clean first, then learn. It removes the topological confusion. It resolves the ambiguity of the overlap region before the classifier ever sees the data. By removing those intrusive samples first, you prevent the model from needing to overfit to them, which allows it to learn a much smoother, simpler, and more generalizable boundary.
So it's not a replacement for cost-sensitive learning.
Not at all. It's a complement. You can, and probably should, use both. Clean the geometric space with GMR, and then train a cost-sensitive classifier on the much cleaner data. You get the best of both worlds.
Okay, that makes a lot of sense. So the theory is sound, the logic is compelling, but does it actually work in practice? Let's move to Section 5, experimental results.
This is where the rubber meets the road. They did a massive validation study. 27 benchmark datasets from public repositories.
And they didn't just compare it against one or two methods.
No, they compared it against 18 baseline methods.
Yeah.
All the flavors of SMOTI regular, borderline, ASN, all the classic undersampling methods, near miss, NCR, EN, you name it, they tested against it.
And they use 7 different classifiers on top of that.
Right. Everything from simple logistic regression and SVMs to ensembles like random forest, gradient boosting, and XGBoost. The whole point was to prove that the benefit of GMR is classifier agnostic. It helps everything.
And the aggregate results were, well, they were pretty impressive.
They were. Across all 27 datasets and all 7 classifiers, GMR achieved the best average rank. It was 4.22, where a lower rank is better. It was the most consistently high-performing method.
It was especially dominant with certain types of classifiers, right?
Yes, it absolutely crushed it with K-nearest neighbors, where it ranked #1 overall, and it was also #1 for decision trees.
Which makes perfect sense when you think about it. KNN is an algorithm that relies entirely on local geometry and distance, which is exactly what GMR is designed to optimize.
And decision trees are famously sensitive to noise in the data, especially at the split points. A few noisy samples can completely change where the tree decides to make a split. GMR smooths out that noise, leading to more robust trees.
But we should talk about the nuance with XGBoost. It's a really interesting result.
It is. So for XGBoost, GMR ranked #2 overall, which is still great, but the none baseline, just doing nothing and feeding the raw data to XGBoost, was actually slightly better on average.
So why is that? Why would doing nothing be better than this sophisticated cleaning?
Well, XGBoost is an incredibly sophisticated algorithm in its own right. It has powerful built-in regularization like L1 and L2. It can handle weighted data natively through its scale post-weight parameter. And its tree pruning mechanisms are extremely robust to noise.
So in many cases, XGBoost is powerful enough to find the signal in the noise all by itself without needing the data to be pre-cleaned.
Essentially, yes.
Yeah.
The authors are very honest about this. They note that GMR was still the best sampling method for XGBoost. So if you had to do some kind of pre-processing, GMR still beat SMOTI and EN and all the others. But yeah, for a really robust boosting model like XGBoost, the marginal gain from pre-processing is just smaller.
The paper also explores a very modern, very cutting-edge application, integrating GMR with tab-DDPM.
Tabular denoising diffusion probabilistic models. Yeah, this is really cool.
So these are the same kind of diffusion models, like stable diffusion for images, but adapted to generate synthetic tabular data.
Right. And the standard way to use them for imbalanced learning is to train them on your minority class and then use them to generate new synthetic minority samples.
But the authors here had a clever insight. What if you applied GMR before you train the diffusion model?
The logic is simple. Garbage in, garbage out. If you train a generative model on your original noisy, topologically invaded minority data, it's just going to learn how to generate more noisy, topologically invaded data.
It'll learn to replicate the problem.
Exactly. But by applying GMR first, they clean the manifold. They gave the diffusion model a rectified data structure to learn from. And the results showed this worked. It significantly improved the quality of the generated synthetic samples, which boosted the final classifier's AUPRC on overlap-heavy datasets like CovType and Yelp.
But as with XGBoost, there was a really important exception, the credit card dataset.
Yes, for that dataset, applying GMR before tab DDPM actually dropped performance slightly.
And this gives us a critical insight into the kind of problem that GMR is actually designed to solve.
It does. GMR is a tool for fixing problems of overlap and intrusion. But the credit card fraud dataset often presents a totally different kind of topology. Fraud cases often aren't overlapping with non-fraud cases. They can be distinct, bizarre outliers. They're like little islands of strange behavior in a vast sea of normal transactions.
And if they're islands, they don't have intrusive majority neighbors right next to them. They're often isolated.
Right. And if that's the case, remember GMR's strict majority cleaning rule. If GMR is too aggressive in cleaning the normal space around these isolated fraud islands, it might accidentally remove valid contextual points that a model would otherwise use to define the boundary of what normalcy looks like.
So it's a specific tool for a specific job.
It's a tool for topological overlap. If your imbalanced problem is purely about rarity, without overlap, meaning the classes are easy to separate but one just has a very low count, then GMR might be overkill and in some cases maybe even slightly detrimental.
Finally, just to round out the experiments, they even applied this to image data embeddings using CFAR 100 LT.
Yeah, long-tailed CFAR 100. They didn't run it on the raw pixels, of course. They took the high-dimensional feature vectors from a pre-trained ResNet 32.
Which proves that GMR operates on the learned manifold itself, regardless of whether the raw input was numbers in a table or pixels in an image.
And by cleaning that feature space with GMR, they were able to outperform standard deep learning techniques for imbalance, like class balanced loss. It really validates their core claim that geometric rectification is a universal concept that applies to any feature space.
We're getting close to the end of our time. Let's try to summarize the big takeaways here. For me, the headline is that GMR forces us to shift our whole focus from counting to geometry.
Absolutely. It's not about how many points you have, it's about where they are and how they're arranged.
And tactically, it does this by replacing the naive one-person, one-vote KNN scheme with this much smarter geometric confidence estimation,
which uses inverse distance or cosine distance to get a high-fidelity reading of the local topology.
And then it replaces symmetric cleaning with adaptive asymmetric cleaning,
driven by those alpha and beta thresholds, the alpha-beta inequality.
And that asymmetry, I think, is the single most important takeaway for anyone listening. If you take nothing else from this deep dive, take this. Your data cleaning and pre-processing pipeline must respect the asymmetry of your cost matrix.
It has to. If false negatives are more costly than false positives, which they almost always are, then your pre-processing has to be stricter on the majority class and more conservative on the minority class.
Stop treating the classes as equal citizens in the pre-processing stage.
They are not equal citizens. One is abundant and disposable, the other is scarce and precious. Your algorithm needs to know that.
I want to leave our listeners with that provocative thought we mentioned at the start, the one from the outline. We've spent this entire time talking about binary classification, majority versus minority.
It's a simple case.
But the real world is often a messy multi-class problem.
Right. You might have 5 different classes, and their counts are something like 1,500, 250, 10.
So in that scenario, class 3, with 200 samples, is a minority relative to class 1, but it's a huge majority relative to class 5. The concepts of majority and minority become relative.
So how does a framework like GMR adapt to that? Do you need a dynamic alpha and a dynamic beta for every single pairwise class boundary?
That has to be the frontier, right?
I think so. You'd need what you could call a relative topology. For any given point, you'd have to calculate the local imbalance ratio based on the classes of its immediate neighbors.
And then adjust the cleaning thresholds on the fly.
Right. If a sample from Class A is in a region where it's overlapping with Class B, and Class A is the local majority in that specific spot, it gets the strict alpha rule applied to it. But if that same sample from Class A is in another region overlapping with a huge Class C, then suddenly it's the local minority and gets the protective beta rule.
A locally adaptive, relative geometric rectification. That sounds like a fantastic title for a follow-up paper.
I would definitely read that paper.
Thank you for joining us on this deep dive into geometric manifold rectification. We hope this gave you a new and hopefully more powerful lens through which to view your imbalanced datasets.
It's not just about the numbers anymore. It's about the shape.
We'll see you on the next deep dive.
Thanks for listening.